distinguished speaker, Dr. Koilian Raidumia, Associate Professor, Department of Chemistry, IIT Guwahati, and Dr. Sumit Dandapad, sir, Postdoctoral Fellow at King Abdullah University of Science and Technology, Saudi Arabia, who will be sharing an insight into their expertise area in the field of science to explore career opportunities. We are indeed privileged and honored to have our speaker along with us today. Our first speaker is Dr. Koilian Raidumia, sir, who is currently working as an associate professor in the Department of Chemistry, IIT Guwahati, Assam, India. His current research efforts are focused on the creation of multifunctional nanofluidics devices fabricated by using only scissors and papers of reconstructed layered materials. He is also working on eco-friendly synthesis of cheap and renewable materials for energy storage and hydrogen evaluation. He has research experience as postdoctoral fellow at Material Science and Engineering Department, Northwestern University, Evanston, Illinois, US, under Professor Jiajing Huang. He has completed his PhD at Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, India. During his PhD, he has contributed towards the synthesis of several new nanomaterials, including graphene analogs of BCN and BN. In addition, he has experience of setting up new reactors for chemical vapor deposition, aerosol synthesis, and fixed bed catalytic reaction. Prior to this, he has completed MS Engineering at Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, India, and MSc Chemistry at Department of Chemistry, Guwahati University, Assam, India. He has an extensive research experience and published more than 59 research papers in reputed journals and has achieved more than 3,000 citations. Before I hand over the session to the speaker, I would like to add that queries are most welcome and can type in the chat box and will be entertained right after the speaker completes the session, as it will facilitate us for the smooth conduction of the program. With this, I hand over the session to Dr. Raidumia, sir. Sir, please.
Okay, thank you, Primli Madam. Thank you for the extended introduction. Actually, when introduction became very long, it's a pressure on the speaker to stand up to it. So I would also like to thank all the organizers for giving me this opportunity to interact with the students, and particularly our Shirantan Bhagwati sir. So as I can see that we have, I'll just share my screen, speakers from like all branches, and I think mostly students are in the level of BSc and MSc, not directly into the research, right? Am I audible?
Yes, sir.
Yes, sir, you are audible.
Okay. Most of the students are in the BSc level, right? BSc or MSc level.
We have students from different backgrounds, BSc, MSc, as well as research scholars, sir.
Okay. So I have targeted prepared my presentation in a by removing most of the technical details so that we can attract students towards this field of research and without scaring them at this with detailed technicality. So let's see how it goes. So if you have any questions or concern, or if you cannot hear me properly, please let me know anytime during the talk. Okay. So the title of talk I have decided to speak today is the magic of structure property relationship by taking layered materials as an example. Okay. So before going to my actual talk, I'd like to thank all the people who is behind the findings that I'm going to present in front of you, all my students who worked really hard so that I can present something or talk something to you, and also funding agencies. Without their help, nothing would have been possible. Okay. So just to introduce you all, like at IIT Guwahati, we are working in a broad area within chemistry that is called material science. It actually involves different branches of science, not only chemistry, which involve physics, chemistry, and mechanical engineering, as well as chemical engineering. So to introduce you to material science, what we do, we go to different materials and go to different levels like molecular level, nanometer level, or micrometer level, and tune their structure. As you know, when you tune out the structure of anything, its property changes. And once the property changes, we get new properties depending upon the new structures. And based on these new properties, we try to find out suitable applications or interesting applications for the same kind of materials. Just to give you an example, how this structure property relationship works. For example, you want to make a building, or let's say a concrete pillar. You all have seen this construction of pillars out of rod, iron rod, cement, sands, and stones, right? We have all the materials, but we just don't dump that in one place. We maintain a particular structure. We make a particular structure of the rod. Then we mix them in equal composition, like a definite composition of cement, sand, and stones, and pour it there to get a different structure. It's not it. And based on the way we are arranging these items or these ingredients, we can get different strength of the pillars or whatever thing you are making. It's not it. If we just bundle all the iron very tightly one upon another and put all the cement and sand and this concrete mixture, we won't get a proper strong pillars, right? We have to fix them in a particular structure. Then we have to put all the mixture, and we'll get the strength. Like that, the strength of the pillar is coming not only from the ingredients, also the way we are arranging them, the way we are fixing them in their particular places, the structure. Like that, even if we do to our molecules or materials in the different length scale, the way they are arranging, the way we are handling them, their property changes. And with that, we can do many interesting things. For example, in the area of smart materials, nanofluidics, sustainable energy harvesting, water purification. So I will show you some of these examples. I will try to avoid the technicality as much as possible. So let's begin with something very simple that everybody we know, the soil, right? Soil is everywhere. Every day we have to deal something with soil. So soil is as you know, is a mixture of lots of living and non-living objects. It's a very complicated system, although it is available everywhere. It's very difficult to find out the exact composition. It changes with place, with time, with seasons. So if we leave out the living organism like microbes and all bacteria and everything, we have non-living object. Among non-living object, we can differentiate it to inorganic minerals, organic matters. Even inorganic materials, we have different parts. So let's take a very simple example of clay. And we have different kind of clay. Clay also different parts of there. We just take two simple clays, which is like one can be called vermiculite, another is montmorillonite. Even if we zoom into the clay, very details, they have a structure of this kind of layer of, there are layered materials. Layered material in the sense, if you go into their crystal structures, they are arranged like a layering of some sheets, like a book. In the book, we have layers of pages, right? One pages is stacked upon another page is stacked upon another, like that. If you zoom in this clay, they also have many layers. They have one within the layers. Also, they have three layers. One tetrahedral layer, like two tetrahedral layers sandwiching one octahedral layer of some oxides, and tetrahedral layers are typically silicate. Okay. Now this vermiculite and montmorillonite, they both are clay. They both have similar structure. One is octahedral and two is tetrahedral, and these layers are separated and stabilized by some metal ions as well as water molecule stay between the layers. Okay. One is simple difference, very small difference between these two clays, like in vermiculite, we have some negatives, this red negatives sign kind of things are representing a negative charge. So this negative charge of two layers will repel. So material will not be very stable. So we have positive charge metal ions between the layers, and this positive charge metal ions will attract this negative charge, and we get a stable materials. Now, what is the difference between these two is like in vermiculite, we have most of the negative charges are on the surface, only very few are in the inner layers. On the other hand, the other clay, montmorillonite clay, most of the charges are in the inner layers, very few are in the upper layers. So what happens when less charges at the upper layers, they can easily expand. That means the attraction between these layers and the metal ions that attract the charges are not very strong. If you put any solvent or water molecule, they will easily expand, they will take more water into it. On the other hand, in this vermiculite clay, as they have more charges on the surface, they attract very strongly to these metal ions inside, and they are very stable. They don't expand very easily. So they are a very small difference between these two type of clay. So we can make use of this small difference to do very interesting things. For example, if you isolate these clays, they look like this. In montmorillonite is a powder kind of things, and vermiculite little bit big particles, this powder. So we can do a chemical treatments, like you can stir them with sodium chloride and lithium chloride at boiling temperature for very long time. Then we get a dispersion. I hope I'm audible. Okay. So it is okay. If any disturbance, please let me know. Okay. So once you exfoliate them, exfoliate means what? We had layers. This, even though we are naked eyes, we are seeing these are the small particles. We don't know what's there. But when you exfoliate it, that means we remove the layers one by one. The solution is like these clays are. Suppose this is a book. In this solution, we have removed the pages one by another. And if you zoom in very at a high, using like electron microscope or atomic force microscope, these have like capability of seeing things beyond our human eyes capability. We can zoom it many thousand times more than our eyes can see. If we zoom in, we can see this kind of flakes to the sheets are there in the solutions. So these sheets are just like a 1 or 2 nanometer thick, but width, like length or width, is like a 1,000 or 10,000, even 1 lakh nanometers. It's like our bed sheet or like a big piece of cloth where the width dimensions like length or width are very big. But if you measure thickness, it is just 1 mm or 2 mm, right? Our like normal clothes and everything. This, if you go to nano levels, you can see this kind of sheets. Now, if you allow to settle them again, once you exfoliate them into 2D sheets, then allow to prepare sheet one upon another these sheets, then they give us a freestanding membrane. We change the structure from powder to this membrane, freestanding membrane kind things. Okay, both the clays can be prepared in this membrane. Now we can also make this membrane one upon another. One place at the bottom we have vermiculite one, in the top we have montmorillonite. Remember, vermiculite do not want to expand, but montmorillonite want to expand whenever we subject it to any external stimuli. Now, if you do that, we get a very interesting property. For example, at this panel, you can see, moment we apply any solvent or vapors, one want to absorb, another doesn't want to absorb. So it gives us a smart material. Every time you do this, they will respond similarly. This moment we apply some solvent, it will it will move in particular fashion, and not only particular fashion, it will move exactly same speed every time you expose it to methanol vapors, acetone, whatever. It will clearly identify what solvent you are exposing, as well as like at that particular solvent, it will bend or come back to original position at particular speed. Similarly, it can also sense heat. It is so sensitive, even if you touch it, it can change the warmth of your body and change its shape. And moment you take it out of your body, it will again go back to original shape. Similarly, there are lots of interesting properties is shown. I'm not going to all the details. And we can also make them a small robot kind of things. You can put them some weight on top of it and expose it to different vapors, regular intervals, so that it can walk like from one place another by transferring some material. Now, thing is like why we need this kind of materials, which movement or shape we can control externally without touching it or without doing anything it. I'm not showing it, but this material can be also tuned by exposing it to light or heat or electric voltage. So these kind of material can be used to handle samples remotely. So why we do need such things? Because there are certain places like radioactive materials or like a very biohazardous samples like coronavirus samples, all these things. We need some machines to do these things for us, analyze these samples. We need to do research on that. At the same time, we don't want any human being to expose to such hazardous systems. So this kind of material can be used to make some devices which will handle those samples for us. Similar device can be also made with another materials where we have like vanadium pentoxide, where we can have one side we have prepared this membrane with 2D sheets, nano sheets of vanadium pentoxide, and the other side same material with belts. Basically, we need two materials which respond differently to different external environment. So here again, if you do lots of things are there. I'm not going to technicality again. With light and voltage, we can tune its behavior. So this is one part of the research where we can do lots of innovation and very interesting field. A student can be interested doing this kind of thing. Similarly, as I said, sorry. So we can make these devices by applying electric voltage. We can tune their shapes and size, and we can tune their surface such as way, then they can take out very small amount of sample and do the chemical test. Here we are showing like a acid based or any kind of disease kind of samples can be analyzed by simple test. That's by we don't have to touch anything, just manually we can move this substrate, and manually this arm can be allowed to touch the and pick up some liquid and go to the testing place where we can place something. Similarly, we can also carry out some chemical reactions where we don't want human involvement. This can automatically move the samples by using a motor or something remotely. Similarly, this handle can lift and things and do things. Similarly, same thing can be done with like measuring. You have a liquid, any some high value liquid. If you want to see there is any contamination or something, you can place this sample inside that liquid, and if there is any impurity or something, it will change its shape. For example, here we are showing it is in acetone, it moved in certain direction. Moment we contaminated the acetone with water, its shapes can be changed. So we can detect the impurities present in the liquid samples without using any chemical sensor. Just by visually we can inspect if there is any problem with our liquid samples. So some other fun thing also we can do by playing with their structure and property relationship. For example, here I'm showing again one of the clay samples. I explained that the attractions between the sheet is controlled by this metal ions. This is positive charge, this is negative charge. So the attraction between metal ions and this negative charge is the why they are stacking one upon another. Now, if we change the metal ion here, for example, typically here we have lithium ions. Then if we change the potassium ion, the attraction between negative charge of the surface and the ions present here changes. Now, if you give any solvent or something, this attraction changes, so we can play around there. If you want something very strong attraction, we can put something like potassium or magnesium 2+ or calcium 2+, which will hold this sheets very strongly. Similarly, if we don't want them to very strongly attracted to each other, we can put something like lithium, which have not very stronger attraction between the sheets. By doing that, what we can prepare a material that can self-heal its damages, just like our biological system, like a tree or our skin. If you make a damage, and if you do the proper environment, proper treatment, after some time, it will be automatically healed. For example, we have taken a membrane surface, we punch a hole there, we placed little bit of water, then this hole is automatically vanished after like a 2-3 minutes. Similarly, if we cut this membrane to half, place them together, put a small drop of water, some 30-40 microliter of water, we wait for some time, it healed. Now, if we try to break it second time, it will not break where we joined. If the joining becomes stronger than original material, it will break it some other place. Then again, we can heal and put that. The same video is showing here, like this region we have a healed, that means we joined. When we try to make it join a different place. This can be seen also from this stress strain curve. This curve is typically shown the mechanical strength of the material. Here you can see the black one is like before any healing, as it is the membrane, pristine membrane. Similarly, second red one is after we join them, that is healed membrane. Here again, there is no compromise in the mechanical property. We can cut and paste. Again, if we make any device out of this material accidentally or due to some reason, this device broke it out in 2 pieces, no problem. We can just put them together, put a small drop of water, it will be fixed again. So this kind of property we can achieve just by simple playing with their structure or the chemical structure or physical structure of the materials. Now I will go to a slightly different topic, that is energy. We all know, right? Their energy is the issue. Everybody want green energy because energy is getting so much other problem like a global warming or like environmental issue. The climate, the planet is becoming so hot. So we are always facing this problem, so much energy problem, because most of the energy we are taking from the fossil fuel, which are very much polluting and harmful for the environment. So many experts think that one of the best way to solve this energy issue is decentralization of the energy sources. So what it means, like instead of the current process where we produce energy in certain places, then we transfer it through wires or something like a big cables to every household. And during the transportation and all these things, lots of energy is wasted, accident take place, and it's a very tedious process. Instead, if we decentralize this energy source, instead of, so what it means, like instead of buying energy from the big plants, if we can have sufficient devices where every household, every person can produce their energy in their home. Everybody can make some small amount of energy in their home, and the excess energy can be sold or given to the places where more energy is needed. It will drastically change the economic scenario related to the energy, as well as it will create so many new jobs and everything. Like it's a greener solution. Now, to achieve this decentralization of energy, what we need to do, we need to have so many small devices where we can make small energy, every household, every stock, every different ways, which people will buy, whichever way suits them. So only one way is not sufficient, because if we buy solar, it will work only in certain places, certain environment. Or if we buy some wind energy, it will again work in certain places. So we need different kind of devices where every places can be used, and people have choice. So that I want to use this one, I will go for by this process of producing energy, so on. So whenever we think about producing energy in a greener way or sustainable way, always people use water, flowing water, or like a mechanical property of the flowing water. And this image was taken from this Mesopotamia civilization, which is around 400 BC, nearly 6,000 years from now. There itself it is shown that mechanical energy of the water is used for different applications, like lifting heavy object, grinding or milling grains like a wheat, rice, everything. So mechanical energy of water is a well-known process which can be used to harvest some energy. And we all know these big dams where are used to produce electricity. And as of now, almost 16% of the total electricity worldwide is produced coming from our big dams. But the problem with dam is like it cannot be put everywhere. Only in certain places we have certain natural requirement, as well as it's a challenge to the people or animals whatever living nearby. It is always a big threat to have such big dams. So now it cannot be used to decentralize the energy process. There's an alternate way which was conceptually presented or proved as early as 1965. Very early on, people knew there is an alternate way of producing energy from flowing water. That is, if we push liquid to very small channels like in nanofluidic channels, then it leads to some separation of charge, and this charge separation can convert it into electricity. So I will explain here little bit details. For example, we have any solid surface of a pipe. Okay, if we tune the structure, or like any surface has some charges, if you tune the structure, the charges can be increased or decreased. Suppose we have a solid surface that is negative charged. What it will draw, it will attract the positive charge towards it, and it will repel the negative charge. And there is a certain distance up to which this charge separation takes place. Okay, so just to remember, if we have a surface, it can attract either positive charge or negative charge. If it attracts positive charge near the surface, we will have more positive. Away from the surface, we will have more negative. Now, almost any pipes, no matter how big or small, we have a small charge separation near the surface. But this takes place very small region, nanometer region, very small. So in our big pipes, water pipes, even though this effect is there, it is almost negligible. Nobody even cares about that. Okay, this is so small. Like this, we have most parties like white region where there is no separation, only little bit of this gray or brown regions where the charge separation takes place. But if you bring this to surface close to each other, like nanochannels, what happens? Most of the surface is covered by this brown region. It's very small channels. Now through these channels, only one particular ion can go through. Okay. Now this charge separation become very significant. Now if we allow liquid to pass through, either positive can go or negative can go. If positive goes, at the bottom we have more positive, and the top we have more negative. If we use this properly, then we can get some energy. And because it is nanochannel, in one nanochannel we may not get a sufficient energy, but size is very small. We can combine in a 1 centimeter cell, we can combine thousands of or lakhs of channel into that. So overall effect is very high. So we can get a significant amount of charge. But the problem with, like, even though it was known 1865 itself, till now no commercial device has been there. There is a problem, because if channels are very small, it is very difficult to push water through it. We need to have very high amount of energy required to push water through it. So because of that, we tested it for a small channel. We get a very small amount of energy. You can see as well, as long as we have to put a pump there. As long as we put the pump, the voltage increases, and as long as we put off the pump, the voltage decreases. We get this energy, but it's very small. Similarly, if we use bigger channels where water can easily go through it, and then we don't get any energy. Because of this trade-off, like channel and this one, we don't get much energy. Okay, I'm almost finishing up my time. So what we can do, we can stack many spheres in it. Like if you take any higher secondary level chemistry course, we know when we take monodispersed spheres and allow to stack them together, they take some close packed structure. They don't arrange randomly. They arrange a very specific manner, and within that arrangement, there are some holes, as I can see from these videos. And these holes are also connected through a specific manner. Like each tetrahedral is connected to 8 octahedral holes, 8 octahedral holes is connected to 4 tetrahedral, so like this. And between these holes, they're connected through this biconical pores shown in these figures like this. Now it is well known in the literature, people have done various research, theoretical as well as experimental research, and shown that if you push any liquid through this kind of biconical pores, it can easily go through it without much hindrance, as well as we can also has this trapping effect which will lead to the surge separation. To use this kind of system for energy harvesting, what we have prepared, so many spheres we have prepared of different pore sizes and stack them together inside a syringe kind of things. Now all this between these spheres, these are all made up of silica spheres. We have small channels which are uh, between tetrahedral and octahedral holes, and if we push liquid through it, we can get a very high amount of energy as compared to previous one, at least 100 to 1000 times more energy we get. And this is what we have shown, like moment we put water, we get energy, moment we leave, we don't get the energy. Okay. Similarly, different spheres we have tested, and we got highest energy with this 1750 nanometer size spheres. Like that, using this system, we can get many interesting behavior where we can just put a small bit of water, and moment water is pushing through this pump, we have a separate container where to put water, so that like water coming out of our water taps from our household is not affected, the flow is not affected. We can do our daily work, washing clothes, giving water to gardens, and taking bath. That will not be affected. But if you just put a little water sideways, we can get a good amount of energy here. Same way, we can just put some water through it, we can get sufficient energy to run small electric devices like calculator and everything. And sometimes if we are free at home, we can also make some kind of device, or for kids to play some devices where they can put on and off and to get some energy. So similarly, like this will not definitely going to save all the energy problem, but little bit of energy, extra energy without wasting anything. Because anyway, water will be always using every household every day. So much of water is used through the taps. If we connect these small devices, little bit of extra energy will produce, which will be at least sufficient to charge a mobile or do small things. And if we have many such devices in house, it will definitely give a contribution. So with that, I would not like to extend it many further, because my time was there till 7:35. It is already 7:33. Just giving you a very another area, a very brief area where we can, we all know that like heat is a universal source of energy. From the very prehistoric time to now, we are using heat everywhere. The problem with heat energy is like whenever we use heat, let's it cooking or like a big industry or rocket everywhere, only 30 to 40% of heat is used for work. Other 60% or 70% is wasting just by heating the environment. For example, you are making a cup of tea, only 30% of energy from the gas, burning gas, is heating the water. Rest is used to heat the container, surrounding air, burner, everything is used. Now, because heat is so vastly used, some of the energy wasted during the heat engine can be, if we harvest, it will be a huge amount energy will be saved. And based on this technology also, like already people are working very long time ago, like more than 150 years, people are trying this, but still not very successful. And I'm not going to explain all of this because of the lack of time, but we have made some device where we can still harvest some of this and wasted energy. Just to give you a quick example, in this device we have shown that like if it's a hot cup of tea or coffee made, like after making this hot food, always we keep it in a dining table, right? For keeping this table, we have some coaster kind of things where we keep it such that it will not affect our tablecloth, or if it's made up of glass, we put something on top of that, we could keep the hot food, right? And if we put our device next to a hot food or hot anything hot, we can get some current and voltage, which can be again used for this one, because we are anyway making so much of hot food, and anyway we are keeping it, we are eating it. Just by using this device next to a burner, next to a cooker, or next to something, we can still get some energy. So with that, I would like to stop you here, and I'll be very happy to take any questions or any concerns or anything you have for me. Thank you very much. Thank you. Okay, I hope I was audible in most of the
Yes.
my talk. Yeah. Because
Yes,
I do
sir,
not
you were
extend my
audible
time.
during.
So yeah. Thank you.
Yes, sir, you were audible throughout the talk. So it was indeed an interesting explanation and talk on the clays, showing the structure and property of natural clay, how it can be used as a smart materials and their interesting applications. Pointing out the energy crisis and how research is going for decentralization of energy, which will further solve some issues like employment and energy crisis as well. Due to its great properties, it can be a solution of energy sustainable solution, making it into a green art solution. So uh, if there is any queries related to this talk, yeah, we have got some questions in the chat box. Yeah. The first one is from Ajit Kumar. Sir, whether we can use this type of clay materials in finding of presence of water in other planets?
Okay. Thank you, Ajit Kumar, for the nice questions. So actually, finding water in other planet is a completely different area of research. It's a space. Uh, Science is a complete different area, but definitely, if we know that water is there, this kind of clay will definitely show these properties. But getting this kind of clay and seeing their behavior in outer space is a completely different area of research. But I would like to say one interesting thing. This clay is dependent upon the nature of water or minerals present in the area. And in the Mars, people have collected some, tested some of the properties there, and they have seen similar vermiculate, monomer, this kind of clays are also present in outer space. So definitely, if we can go there and see, this clay will definitely help. But only thing like I don't know how to go and test in the outer space and see this.
The next question is from Nikita Devgupta. Is there any devices with such properties which can be manufactured to remove or detect any poisonous substance from a material surface or a solution?
Okay, thank you, Nikita. So so far we have tested that we can detect certain certain contaminants or poisonous substrate in the solution or vapor state, but we are not yet investigating the removal part. Detection and removal are two different area of research. So far we have focused only on detection part. At least we can say this water is contaminated. How to purify this water or this material or this substance, that's a different area of research.
The third question is from Pritam Phukan. What forces control the attraction between clay sheet?
Okay, Pritam. So as I discussed, I'll repeat. So clay has negative charge. All the clay layers are negative charge. So negative will repel. So clay structure will not be stable. So how it is stable? Between the clay sheets, we have cations like sodium ion, potassium ion, magnesium ions. These positive charge ions are attracted to the negative charge of the clay surface. And this attractive force between the cations and the negative charges of the clay surface controls the force of attraction between the clay sheets. And if we somehow change this ion, the attractive force or repulsive force can be changed. We can tune that.
The next question goes, are there any important applications of material science in healthcare sectors? Question has come from Jerin Sabnam Ahmed.
Okay. Thank you, Zerin. So there is huge application in any sector, including healthcare sectors. For example, healthcare devices. I have seen people are preparing devices to detect different diseases, or simple by analyzing their breath, their blood. Nowadays, so many devices has come out. Different people are working. Although I am not working in this area, but I can see there are many devices coming out of material science, this structure property relationships. We can determine, detect diabetes and other diseases based on device made up of materials. And material science is an area which has affecting almost all sectors. Similarly, we can also have controlled delivery, drugs delivery in specific regions. We can also, now people are preparing smart bandage where we can put in your body. It will tell you whether, without removing the bandage, it will tell you whether wound is healing or something bad is happening, or such a way that if its wound is not healing, it is getting worse, it will automatically inject some medicine to the wound without any human interference. Nurse doesn't have to open it every time and see. It will automatically detect if any liquid is coming out of the wound, that means wound is not healing, then it will inject liquid, or whatever medicine is there, it will directly inject. And if it is already healing it, then it will not inject that medicine. Such kind of things are also coming out in the healthcare section. I hope I have answered your question.
Can we use organic product to remove poison material? By Sangeeta Chakraborty.
Yeah, Sangeeta. Yeah, thank you. So there are so many products actually. Nowadays, research is such a is going on such a big way. So many people are involved in doing research. So all topics are like thousands of people are studying. So removal of poisonous material is a very important and a hugely studied area of research. People are using organic materials, carbon-based material to remove this product. Unfortunately, I am not one of that, but I can see many papers coming out in this area. Only thing like I have just seen, I'm not an expert of using organic products to remove poisonous materials, but it is definitely, there are many people are working in this area.
I guess this is the last question from Stutrika Bhattacharjee. Can we classify Wolverine material as a self-healing material?
Okay, thank you very much, Shrutina Bhattacharjee. Actually, unfortunately, I don't know what you are meaning. I don't understand Wolverine materials. So if you can give some details about it, probably I'll be able to explain you. But otherwise, a self-healing phenomena I have explained, but I don't know exactly what you are asking. I'm sorry.
Okay, it expand. You wrote it expand when damaged.
Yeah, then definitely it should be working, but unless and until I see it, I know it, the material I studied, it is be not a very matured way of answering it. So I just heard it, probably I'll go through it and see.
Okay, sir, the one question has come up. Sir, in what common ways can we observe decentralization of energy sources at the most common level?
Actually, till now, we can say solar energy is one of the way, because different household can install solar energy panels. Then even I know, like even Assam Electricity Board also accept, if you have a big panel using extra energy, then you can give some of the energy to them. But there is many issues like cost of the panels as well as lifetime of the panels, which is not sufficient to give this one. Again, it is again weather dependent and place dependent. Similarly, wind energy is also there, but there is a long way to go. Still, like 99% of the energy are coming from our, not 99, I can say around say 70 to 80% energy is coming from this non-sustainable way. But decentralization is even more, like 90% of energy is not decentralized way it's coming. It's a long way ago, it's a concept. Slowly people are working on it, but it will take time.
Thank you, sir. I hope all the participants has benefited with this talk, as energy is one of the most important factor for a country to become a self-sufficient. And sir has shown us some very simple ways to generate energy, which is really great. That The ways you have shown, sir, are very simple and that even the children can try them with
Thank you. Thank
their
you. I
innovative
hope students will be
ideas.
motivated to try out something at their home, as well as they will motivated to pursue science in their next level of education.
Yes, sir, sure. I hope they got motivated, and really it was an interesting talk. And the students can take up more research on that.
Thank you. Thank you.
Thank you. Thank you so much, sir.
Thank you, madam. Thank you. Okay. Okay, then I'll leave then. Thank you.
Thank you, sir. Coming to an end of our first talk, now I would like to welcome our second speaker, Dr. Sumit Dandapat, sir, who is currently working as postdoctoral research fellow at King Abdullah University of Science and Technology, Saudi Arabia. He had a sound scientific and technical caliber in numerical ocean modeling. Dr. Dandapat has completed his PhD in physical oceanography from IIT Kharagpur, India. During his PhD research, he has worked in numerical simulation of interannual variability of Bay of Bengal. Thereafter, he has worked as project scientist in Indian Institute of Tropical Meteorology, Pune, India. He has profound working experience in regional ocean modeling of Indian Ocean using different ocean models. Prior to this, he has completed his master from Tezpur University, Assam. He has around 13 research publications on ocean modeling in different recorded journals. Over to you, sir.
A very good evening, everybody, and thank you, madam, for the introduction. So shall I share my presentation?
Yes.
Yeah. Yes, so it will be completely different topics. So it is basically, as madam introduced, that I did my PhD in physical oceanography and ocean modeling on Bay of Bengal. So I will present some work from my PhD and my postdoctoral experience, and try to show what I have done, and also if you have get any interest in this ocean model or this physical oceanography related research, please let me know. So today topic is application of different ocean models in the Bay of Bengal. So I'll first give an introduction of physical oceanography and ocean models. Then I will discuss two different ocean models. One is regional ocean model and is global ocean model. So first is what is oceanography? As you all know, that basically it's a study of Earth's oceans, including the coastal region of the ocean and seas. So basically, oceanography can be divided in 3-4 parts, like physical oceanography, chemical oceanography, biological oceanography, also geological oceanography, we can say. So I work in physical oceanography. And in physical oceanography, basically, we deal with the temperature, salinity, sea surface height, ocean currents, waves. And I do some numerical ocean model and climate change related work. So we all know there are 5 oceans, and Pacific Ocean, Atlantic Ocean, Indian Ocean, Arctic Ocean, and Southern Ocean. And also some seas are there. That seas basically that mostly bounded by the land. So important seas are like Mediterranean Seas, Red Sea, Arabian Sea, even Bay of Bengal, Gulf of Mexico. So in physical oceanography, what we do, basically, 2 things are important: sea surface temperature and salinity from the seawater. And based on that, we calculate the density. So if we see that average ocean temperature is 3.9 degrees Celsius. So, but if you see the equatorial region, here it's nearly 28 degree to 30 degrees Celsius. And obviously in the polar region, it is very less. An average salinity is 34 PSU. That is practical salinity unit. That is basically the measurement of salinity in 1,000 parts of ocean water. So average is 34 PSU. Even if you see that salinity in the equatorial region, the salinity is very low, basically due to the high precipitation. And in the if you see the polar region, there again the salinity is low because there is lots of sea ice is there. So melting of sea ice, obviously, it will increase the fresh water and reduce the salinity. So now, what is ocean model? Ocean model basically a mathematical model of general circulation of ocean. It uses basically momentum equation, continuity equation, and the equations from thermodynamic terms. So what is the application of ocean models? Basically, ocean models like it's used to for the physical process and biogeochemical process to determine this process, coastal upwelling, climate change, for offshore oil industry, even ship route detection, also this fishing zone detection. These are various aspects, various application of different ocean models. Now, I will mention that in the oceans, there basically we all know that like atmosphere, troposphere, stratosphere, different vertical range of atmosphere is there. Like in oceans, there is 3 different layers are there. First is mixed layer, that is basically you can say that is 100 meter depth, and next is thermocline where the temperature gradient is very high, and third is deep water. So this is basically 3 layers of ocean in vertically. And what are the atmospheric forces that affect the oceans? So wind is the most important, and another are like heat flux, net heat flux, and also the gravitational pull for the tide generation. These are important for these are atmospheric forcing for the oceans or ocean circulations, we can say. So we can classify the ocean models in 2 types. One is the global ocean model and is regional ocean model. So in global ocean model, some of the global ocean model like modular ocean model, MOM, HICOM, NEMO, and the most important regional ocean model is like ROMS, regional ocean modeling system, ROMS, and MITGCM. Basically, there are 5 or 6 ocean models are there. So 2, 3 regional ocean model, and 3 are the global ocean model. Generally, global ocean model, since to solve these equations in for these ocean models, it requires a high computational power. So for this global ocean model, the vertical and horizontal coordinate system is simple. Like for vertical, it's a simple pressure based on the pressure difference in the vertical, and the horizontal basically the finite difference method for the global ocean model. But for the regional ocean model, this is used to simulate the coastal process. It is used in offshore in the industry. So for this, some high resolution model are required. That is called regional ocean model. Here the horizontal grid based on basically the finite element method. Also finite volume methods are also used. And the vertical grid are basically sigma coordinate, that is reflect the bathymetry, and it is useful to determine the resolve the vertical processes. So as I mentioned that ocean models generally use the 7 equations, the Navier-Stokes equations, the horizontal and vertical momentum equation, first 3, then continuity equation based on Bosonic approximation, and also the salinity and temperature, there's the equations, and the equation of state. These 7 ocean models are, any ocean models are based on these 7 equations. Also, there is some modification based on that. If you use to determine the biogeochemical process, then we have to add some extra parameter like this, we have to modify according to our requirement. So I will now show the one application from the regional ocean model and another application from the global ocean model. Both are applied in the Bay of Bengal. So this is a regional ocean model system, ROMS. So the ocean models are primarily used to determine the ocean currents. Currents are basically zonal and meridional U and V current. So as I mentioned, again, I am repeating that ocean models, the input are temperature, salinity, and the atmospheric forcings, and sometimes river tide, these are. So these are the things, and the output what we get, basically the ocean current system, and also we will get the ocean current, sea surface height, others. So first I mentioned some of the ocean current, important ocean current in the world ocean. So this red are the warm current, and these are the basically blue are the cold current. You can say that warm current means it will advect the heat from the I can say that equatorial region to the polar region. So these are known as warm current. So one of the most important warm current like Gulf Stream, Agulhas current. So ocean current basically continuous directed movement of seawater driven by wind, Coriolis effect, breaking waves, temperature, and salinity differences. And eddies are the circulation of the current. So it can be eddies, or we can say gyres. If it is the circulations are more than 300 kilometers of radius, we say that it is a gyre, or it is less than like 100 kilometers, we say that these are eddies. So these eddies and gyres are the circulation of currents are very important in the world ocean or the climate. So because it's transport heat, salt, nutrients, and other chemicals, it's regulates planet Earth weather, climate system, marine ecosystem. More than half of the kinetic energy of the world ocean is contained in the mesoscale eddies. So another because thing I want to mention, there is the Indian Ocean dipole. So Indian Ocean dipole is the basically the temperature difference between the Eastern Equatorial Indian Ocean and the Western Equatorial Indian Ocean. So some years, what there is a temperature anomaly is more in the Western Equatorial Ocean. So Western Indian Ocean, they are known as positive IOD events, and when it is the temperature anomaly is higher in the eastern part, Eastern Indian Ocean, these events are known as negative IOD events. So these are something related to the ENSO and El Nino events. So if I see that some years like 2000 in recent years, 1997 is a positive IOD year, 2006 is a positive IOD year, 1999 is a negative IOD year, and 2010 is a negative IOD year. So these strong negative and strong positive IOD events have a huge impact on the oceans and ocean circulation, ocean currents. That I will tell how the ocean models determine it or resolve these things. So first, in the regional ocean model that that has been done on the Bay of Bengal, there is a domain of 76 to 100 degree east and 4 to 24 degree north, and it has a horizontal resolution of 1/12 kilometer, and 32 vertical levels are there, and these are some physical parameters there. So here, these are the number of grids, horizontal grids. So here, what we have done that ocean model, and this is ECMWF3 only forcing has been used on the ocean model. And since this is a regional ocean model, so it needs some initial and boundary condition. That means when a differential equation is solved, like it has required some initial condition, and for boundary condition is like that. So that initial data we provide from a global ocean model, and some river input there I put. So yes, these are the heat flux, net heat flux. So in the model, this is basically the latent sensible net short wave and net long wave heat flux, and this is the evaporation minus precipitation term. And these are the like grids in the vertical grids in the ocean model in the Bay of Bengal. So the thing is that the model was run from 2006 to 2012, and so what we have seen that if we see particular 2006 and 2010 here, we can see that, sorry, yes, so this ocean current system along the western Bay of Bengal is completely different at the same month. This is October month. So if we see there are many eddies are there. These are the cold eddies, there are warm core eddies, basically the anti-clockwise and clockwise eddies. But here the eddies are less. There on strong current, on well-developed current is observed. So basically in 2006 and 2010, what we have seen that is a positive IOD year and it's a negative IOD year, as I mentioned. So that means that the IOD has effect and on the ocean current, on the Bay of Bengal current, and how it is. Okay, this is also again that I determined from the eddy tracking how much eddies are there. Like 2006, more eddies are there. 2010, less eddies are there. So what we have seen that the equatorial that the wind, the easterly and westerly wind, that actually generate two pair of upwelling and downwelling events, or we can say that events basically generate the waves. These waves are known as Kelvin wave, equatorial Kelvin waves. So these waves propagate, and this is hit the Sumatra coast and bifurcate here, and it is goes as a coastal Kelvin waves. So what we have seen that the second downwelling Kelvin wave during October-December is very strong. It is goes around all along the western Bay of Bengal and enter the Arabian Sea. So this during October, that current should be strong, but what we have seen that previous figure that this is 2006, there is no such current, only basically is dominated by the small circular eddies, but in 2010 there is a current is there. So what we have seen that when the easterly wind is strong during this is the easterly wind, this is a positive IOD events. When the easterly wind is strong, then basically there is a sea level pressure is less and there is a high temperature is here. So this cause the upwelling events. When the upwelling events are very strong, then what we have seen that when upwelling events are very strong, then it dominates the downwelling events. So downwelling events become weak, but this downwelling event is basically the current system. So what we have seen that during the positive IOD year, this upwelling has become strong and it's dominates the downwelling event and it reduces the intensity of the current, and so there is no such current in the positive IOD year. Whether in the negative IOD year, there's more current is very strong because that time the downwelling events become strong. So this is some example of how the regional ocean model resolve the things. So now what we can use. So this from this ocean models we can determine this how the current system will be there in the coastal process. So whether it will be, so we can forecast, we can the ocean circulation condition, that is upwelling and downwelling condition, that is important for the fisheries and aquaculture and also for the industry. So now I'm going quick with another is the so now I'm going with another application of ocean model, that is a global ocean model. So this is a global ocean model that I worked, and this name is the modular ocean model MOM5. So here I also put the initial condition and three-hourly JRA forcing and river input. So this model has been used to study the impact of rivers. So what I did, that we all know that when there's a strong monsoon is there, so there will be high river runoff will be there. When monsoon is weak, the rainfall is less. That time there will be the less river discharge is there. And Bay of Bengal is very sensitive to river discharge, because probably it is the only basin in the world ocean there is so much river discharge come into the ocean water. So it's a highly fresh water in the Bay of Bengal. Now, so what is the impact? So when the river discharge is more due to the high rain, and when river discharge is less due to the less rain, so what is the impact on the ocean? That we determine using the ocean model. So the river discharge, what I use is the, like, Ganga Brahmaputra River, Iravathi River, Godavari, Mahanadi, Krishna, and this Sitang at the Myanmar side. So these are the main major rivers in the Bay of Bengal. So we picked up 4 excess river runoff year, these 4 years, 80, 88, 90, 2007, and 4 deficit river runoff year, 79, 86, 92, and 2009. And so this is some statistics from the ocean model simulation that we need to verify the model results with the in situ observations, and the with river and without river and the in situ river. So it's matched quite well. And so the results. So what we have seen during the excess river runoff year, we take a composite of the output of the temperature, salinity. So what we have seen, that negative SST anomaly is observed in the excess river runoff years during post-monsoon period. The SST difference in the plume area, basically this is the plume area, we can say that the northern Bay of Bengal, that between the excess and deficit river is 1 degree Celsius. So there is a 1 degree Celsius of ocean temperature due to the excess and deficit river runoff, or you can say that excess and deficit rainfall. And also we have seen that in the plume region, that this is basically the excess river runoff here, and this is the deficit river runoff here, the anomaly. So we have seen that there is a difference of 2 PSU in the river mouths and the river distributed region along the western Bay of Bengal. So we have seen there is a 1 degree Celsius of temperature and 2 PSU of salinity difference. Also, we take one cross-sectional area at 19 degree latitude between the with river model, and we have also seen that in vertically also there is a temperature difference and salinity difference is very significant. So next we determine that how it affects the surface of the oceans. So as I previously mentioned, that basically the ocean surface up to 100 meter vertical depth, we can say it's a mixed layer depth, where temperature salinity are mostly homogeneous. So we can say that this is again the MLDS. So the mixed layer depth here in the ocean, in the river mouth and this plume distributed area, this anomaly is I think, yeah, it's negative. So it is coming 15. It's yeah. So the MLD is very less. Is MLD decreases to 10 meter depth when basically when the fresh water come. So it makes the layer of the fresh layer above the salinity water, and it's a very less of 10 meter, and it's create one barrier layer in between the mixed layer and the thermocline depth. So this barrier layer actually suppress the mixing of the topmost layer and the mixed layer and the subsurface layer. So the what is the result is that the mixed layer decreases during the strong monsoon or the high river discharge region, the top layer. So that also we have seen that the barrier layer is very strong. So now why these are important? So we can say that these are all related to the ocean heat content, like higher accumulation heat is found in the deficit river runoff areas because heat capacity of salt water is more than the fresh water in the salt water. So the fresh water influx in the excess river runoff areas reduce and it reduced also heat storage. And we all know that when the heat storage is more, it will be sensible to the formation of cyclones. So we can say that when there is a deficit river runoff year or the less monsoon year, that time it can trigger the cyclones in the Bay of Bengal. So this way we can resolve the ocean dynamics, also some ocean atmosphere interaction using the ocean model and various different types of ocean models. Yes, that I mentioned that is a it can induce the tropical cyclone formation. So as I mentioned that these are the two example that I mentioned. So there are many different aspects, topics are there that we can study using different ocean model, like climate change, coastal upwelling, tide, tidal events, effects of tide, turbulent mixing in the ocean, also tsunami, internal tides and waves. So these are based on various spatial and temporal scale and this phenomena. So according to this, we need to use the different ocean model, or we need to tune the ocean model. So I hope I give a overview of the ocean models, their applications, and oceanography. So if you have any question or interest in the oceanography ocean models, please let me know.
Thank you, sir. Starting with the basic of oceanography, sir has highlighted how ocean currents and eddies are important to transport heat, salt, nutrients, and other chemicals, thereby regulating the planet's weather, climate, and marine ecosystem. Sir has also pointed out how the ocean models are applicable in solving the standard equation related to the motions, thereby helping out in aquaculture as well as forecasting ocean circulation condition. Because we have a few questions, queries to this. So,
Yes.
till now, we didn't get any queries. Participants, if you have any queries related to this specific topic related to the oceanography, you can kindly text in the meeting. So yes, here we got one question. How is the amount of upwelling estimated? And the question is
Yes. Basically, upwelling is a vertical motion of the water. So basically, we use the continuity equation, and that one equation from the model I show. So from there, from the UV, and basically it's the measurement of W, the vertical lower. So from the horizontal, from the continuation and knowing of the U and V current, the horizontal current, we can determine the upwelling event. And yeah, it is definitely very important for the fishery industries, or because where the upwelling is important, where the upwelling zone is there, the more there is basically the fishing zone.
We have another question. Sir, can the river insertion depth exceed 40 meter, or is it one?
Yes, it's a good
Yeah,
question
limiting.
actually, and so it's actually depends on various means the river discharge amount of the particular river. So 40 meter is a good approximation in the MOM ocean model that I used 40 meter depth. So basically the freshwater mixing, generally we can say that 40 to 50 meters. So beyond that, it's not that much significant. So we try to put most of the, we can say that the freshwater in the upper 40 meter depth only, and we discretize based on that. That basically, so this is 40-50 meter is a standard. Again, we can say one thing that like Ganga Brahmaputra river, this is a huge river discharge. For this, it is 40-50 meter. But for less river discharge, we can put 20 meter depth. That is basically we use.
We don't have any questions. So thank you so much, sir, for a very nice presentations on oceanography. Thank you once again. In the meantime, I would like to request all the participants to kindly fill up the feedback form as well as quiz and submit the same by midnight. So with the end of the interactive session, with the end of the, thank you, sir.
Thank you very much. Yes. Yes, please, ma'am.
With the end of the interactive session, it gives me an immense pleasure to offer the word of thanks as we have come to the end of the 2 days online international workshop on career planning, exploring the recent trends in the ocean of science, jointly organized by the Department of Geology, the Department of Chemistry, and the IQAC Gurgaon College, Siliguri, Assam, in collaboration with the Department of Applied Geology, Dibrugarh University, Assam, India, to mark the celebration of the World Ocean Day. On behalf of the organizing committee, I extend my heartfelt gratitude to Honorable Principal, Gurgaon College, Dr. Habia Hasim Muntasar, for providing all possible help along with guidance and support in organizing this workshop. Thank you, sir. You have always been a constant support. I would like to thank respected Dr. Rina Handik ma'am, Vice Principal, Gurgaon College, for her valuable support and encouragement. I would like to thank IQAC Coordinator Dr. Surajit Saike sir for his constant support and encouragement. Our sincere gratitude to Professor and HOD Dr. Diganta Bhiya and Professor Kalpana Deka Kalija, Department of Applied Geology, Dibrugarh University, for their kind support and collaboration. Sincere gratitude to Dr. Chandraditya Gogoi sir, HOD, Department of Geology, Department of and Dr. Anna Goeman, HOD, Department of Chemistry, Gurgaon College, for their continuous support and guidance. I extend my sincere gratitude to our esteemed resource person, Dr. Kalyan Raidunia, Associate Professor, Department of Chemistry, IIT Guwahati, Dr. Sumit Dandapat, Postdoctoral Fellow at King Abdullah University of Science and Technology, Saudi Arabia. Dr. Ariel Pesner, Postdoctoral Fellow at the Smithsonian Marine Station, US. Dr. Utkarga Adhikari, Dana-Farber Cancer Institute in Boston, USA, which have joined us from different corners of the world, who generously agreed to share their expertise with us. Also, I would like to offer our heartfelt gratitude to the organizing team who work immensely on your watch in smooth conductance of these technical sessions. Last but not the least, I would like to thank all the participants present here and making this workshop a great success. Looking forward to more such inspiring and informative interaction in future. With these warm words, we come to the end of the two-day online international workshop on career planning, exploring the recent trends in the ocean of science. Thank you so much, everyone. With this, we conclude. Good night, everyone.